Hyperbola. As we have discussed about circle, parabola, ellipse, now comes the next conic section, which is hyperbola. As we have discussed in the previous session that hyperbola is the conic section of a bicone, which we have seen when it is cut along the cone, we get the cross section, which is a hyperbola. So that hyperbola is what we're going to discuss in the session more briefly through the mathematical properties. Now, as we know that hyperbola is the locus of a point P such that its distance from the fixed point, which I denote with S, if the distance of this locus from the fixed point S is always greater than the distance from the fixed straight line. That is, if I take the distance from P to the fixed straight line L, then we say the perpendicular distance, then we say that the locus is a hyperbola. That is, if SP, which is the distance from S fixed point to the locus, and by PM, which is the perpendicular distance from P to the line fixed straight line L, is always greater, then we say the locus P follows a path which we call as hyperbola. Is how we get this in the form. That implies is the condition for existence of hyperbola. S being the fixed point, L being the fixed line, and P being the locus, SP by PM should always be greater than 1. Is how we connect the hyperbola with its mathematical inequality. Now let's see the eccentricity of hyperbola conditions. The eccentricity is generally denoted by E, which is nothing but the ratio of SP by PM. Is how we define the eccentricity. And for hyperbola, the condition is that E is greater than 1. Is how we define the eccentricity of the hyperbola. E is greater than 1 for hyperbola. Now let's see the equation of hyperbola. Before we discuss the equation of hyperbola in standard form, it is very important to understand or identify the shape of hyperbola exactly on xy coordinate system. So let's see how an hyperbola looks on an xy coordinate system. Suppose I have my x-axis and my y-axis out here with center as origin. Now an hyperbola looks something like this. It is like a biparabola where I have two parabolas on either side which are symmetric about y-axis. This is the mirror image of this with respect to y-axis. Now as I have my center as origin, my focus lies somewhere here. Then the other focus on the other side lies out here. Is how we identify the focus of these two things. Now as I have this, I take the point P on the hyperbola as this, and similarly I take the point here as P dash. Now I drop a perpendicular from P onto this line which exists out here. So there are two lines. L and L dash out here. And I drop a perpendicular from S to P, which is M, and from P dash to M dash, which is this, which clearly show that SP is greater than PM, because for hyperbola SP is always greater than PM, and hence S dash P dash is greater than P dash M dash. Is how we understand this. So with this, we identify that S dash are called the foci of the hyperbola, the plural of focus. S is the focus and S dash is the focus, and S dash are the foci of the hyperbola. And L and L dash are said to be the directrices of the hyperbola, which we have here are the directrices of the hyperbola. The center is origin. The center of hyperbola is said to be origin 0, 0 is how we identify in this case. And P dash are said to be the points on the hyperbola. So with this, let's define each of the standard form of equation of hyperbola using the basic information of foci, directrix, and origin. Now here, the equation of hyperbola is given by x square by a square minus y square by b square equal to 1 is how I identify the equation of hyperbola in this form, where here I assume a is greater than b and b square is a square into e square minus 1. So these are the two properties through which I define the standard form of hyperbola, where equation of hyperbola in standard form is x square by a square minus y square by b square equal to 1, with a greater than b, and b squared is given by a square times e square minus 1, where in ellipse it is 1 minus e square. Here it is e square minus 1, simply because e is greater than 1. And in case of ellipse, e is less than 1. In case of hyperbola, e is greater than 1, given by b square equals a square times e square minus 1. Equation of hyperbola in standard form. Now here, let's try to identify the coordinates of foci, equations of directrices, and any other properties identified here. Now as I have here my distance, the a is the point which the hyperbola cuts x-axis on the positive side, and a dash is the point of intersection of hyperbola with negative side of x-axis. And similarly, I have b and b dash which exist out here. Somewhere. Now, the distance a dash is 2a, which gives me the property that the coordinates of a are a0 and coordinates of a dash are minus a0, such that a dash is 2a. And then my coordinates of b are 0b and this is 0 minus b. Therefore, bb dash is 2b. And we have the foci which are given by AE, 0, and the other focus is given by minus AE, 0. Is how we identify. And then if I have this as Z, and this as Z dash, then the coordinates of Z are A by E, 0, and the coordinates of Z dash is minus A by E, 0, and center is of course origin. Is how we identify each of the coordinates of S, A, Z, C, Z dash, A dash, and S dash. And comes the equation of directrix, which is given by X equals A by E, and here the equation of directrix L dash given by X equals minus A by B, A by E. Is how we identify each of the coordinates as described out here. The focus, the vertices, the center, and foot of perpendicular of the focus with the directrix, and equations of directrix are all out here. Now let's see how we can find eccentricity as the formula. So suppose I have the equation of hyperbola is x squared by a squared minus y squared by b squared equals 1, with a greater than b, and both a and b are positive, and of course e greater than 1, then we know that the b square is given by a square into e square minus 1. So using this, let's see what would be the formula for E when I make E as the subject in this relation. So to make E as the subject, I expand the brackets on the right hand side, a square e square minus a square, which on further simplification gives us a square e square equals a square plus b square, by bringing a square arranged to the other side. That implies my e square is a square plus b square by a square. That implies my e is plus or minus root of this. But since e is greater than 1, I have e strictly as plus root of a square plus b square by a square, or I have e as root of a square plus b square by a, is how I identify the relation with eccentricity E. Therefore, the eccentricity of the hyperbola is given by root of a square plus b square by a square, or root of a square plus b square whole over by a. The formula for eccentricity using the standard form of hyperbola condition. Now that we have discussed about some of the properties of hyperbola, now next is the x-intercepts and y-intercepts. That is, we would like to identify at what points does the hyperbola cut the x-axis, and at what points does the hyperbola cut the y-axis. So let's see the x and y-intercepts of the hyperbola. So equation of hyperbola being x squared by a squared minus y squared by b squared equal to 1, assumed with a greater than b. To find the x-intercept, I take the condition y equal to 0. So in order to find the x-intercept, I assume with y equal to 0, then I get is what we get when we simplify. That implies x is plus or minus a. It's not root a, it is a. Therefore, the graph cuts x-axis at a and minus a. Therefore, hyperbola 1 cuts x-axis at a0 and minus a0, and therefore we denote this with a and this with a dash. Is how we identify the x-intercepts of the hyperbola. Similarly, let's see the y-intercepts of the hyperbola. Now next comes the finding of y-intercepts. Now in order to find the y-intercepts, we assume x equal to 0. To find x-intercepts, y equal to 0. To find y-intercepts, x equal to 0. So let x equal to 0. Then the equation 1 reduces to 0 square by a square minus y square by b square equals 1. And this, on further simplification, gives 0 minus y square by b square equal to 1. That implies minus y square equal to b square on cross multiplication. That implies y square is minus b square. But this is not possible because root of a negative number is not defined. Therefore, since root of minus b square is not a real number, which indicates that, therefore, y-intercept do not exist. And when y-intercepts do not exist, we understand that therefore the hyperbola 1 given by equation 1 does not cut y-axis. It cuts x-axis at a and a dash, but the hyperbola does not cut y-axis because of this reason. Is how we understand the x and y-intercepts for the hyperbola. Hyperbola has two x-intercepts, a and a dash. Hyperbola does not have any y-intercepts. Now this session is about region of existence of hyperbola because it is identified that there are some regions where the hyperbola does not exist. So let's see what are the regions in which the hyperbola exists and what are the regions in xy coordinate system where the hyperbola does not exist. So in order to identify the region, let me take the equation of hyperbola in standard form. And then I would like to make y as the subject. So that implies y square by b square is x square by a square minus 1. This, on further simplification, gives y square is b square by a square times x square minus a square is what we get when I cross multiply and simplify this with LCM. That implies my y is plus or minus b by a of root x square minus a square is what we get. Now the y value is set to exist, to be real. The value of y is real if and only if plus or minus b by root of x square minus a square is real. And the whole of this being equal is real only when this is positive, because root of a negative number is not defined. And therefore, this is real only if x square minus a square is at the most greater than or equal to 0. So which, on further simplification, gives x greater than or equal to a and x less than or equal to minus a. And this is the region where the parabola or the hyperbola exists. That is, if I take the hyperbola, I always have the hyperbola in the region where x is a0 and minus a0 with a dash and a. So hyperbola does not exist in this region, but it exists in this region. Is how we identify the existence of hyperbola. So this makes me understand the two regions, one this and the other is this, where hyperbola exists and here does not exist. So this is the region where the hyperbola does not exist. This is the region where the hyperbola exists. Is how we identify the relation connected with the region of existence of hyperbola. X less than or equal to a, greater than or equal to a, and x less than or equal to minus a is the region of existence of hyperbola.